Forget flat photos. We're talking about instantly turning a single cluttered snapshot into a perfect 3D model you can walk around.
Yeah, it's like giving your phone camera actual superpowers. Welcome to Artificial Intelligence, papers and concepts curated by Dr. Satya Malik. I'm Jack Malik.
And I'm Sophia Lane. And it's probably worth noting, just for clarity, that both of us are AI-generated hosts. We're here to guide you through some pretty transformative technology.
Which I think makes a deep dive into a new generative model particularly, well, relevant.
I'd say so. So what's the mission for today?
Today is all about SAM3D, a new generative model from Meta Superintelligence Labs. And this one is a big deal.
Okay.
It's designed for 3D object reconstruction from just one image. The main goal here is predicting everything, the geometry, the texture, the layout.
So the shape, the color, and where it sits in the world.
Exactly. Even in these really messy, complex scenes, what researchers call in-the-wild images, where objects are hidden or blocked.
All right, let's just jump right into that. Because 3D reconstruction isn't new, but why is it so incredibly hard when you're just using a single cluttered snapshot, like a messy bookshelf?
Well, it's all about ambiguity. When you take a 3D world and flatten it into a 2D picture, you just lose so much information.
You lose depth.
You lose depth. A single pixel could be a tiny thing up close or a giant thing far away. Traditionally, computer vision needed multiple pictures from different angles to, triangulate the shape.
So with only one image, how does SAM3D even begin to guess?
It uses the same trick we humans do, recognition. We don't just see geometry. We use what are called pictorial cues, shading, perspective, sure. But the most powerful cue is the familiar object cue.
Meaning if I see part of a coffee mug, my brain just fills in the rest because I know what a mug looks like.
Precisely. You instantly know its 3D shape, even the parts you can't see.
And that idea, that recognition unlocks reconstruction. That's been around for a while in computer vision, hasn't it?
Oh, absolutely. The core insight goes all the way back to Lawrence G. Roberts in 1963. He showed that if a machine could recognize a pattern as a known 3D object, it could figure out its pose and shape.
So SAM3D is basically that idea, but supercharged.
Supercharged with modern generative models and just a staggering amount of data. It can generalize to almost any object.
That shift from geometry first to recognition first is it's so powerful. Now, before we get into how they got all that data, which is a story in itself, a quick word for our sponsor. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So we're back. And we just established that recognition needs a ton of world knowledge. And that brings us right to the data barrier.
It's a big bottleneck in 3D research.
Exactly. To train something like SAM3D, you need millions of real photos, each one paired with a perfect 3D model. So why is that so hard to get?
It's just the manual labor involved. It's artisanal. You need a professional 3D artist to sit down and build a perfect 3D mesh for one object in one photo. The paper says that can take hours for one object.
You can't scale that. It's too slow, way too expensive.
So how did the SAM3D team break that barrier?
With two really clever insights. The first was using semi-synthetic data. They call it render paste, or RP3DO.
Render paste. Sounds like what it is.
It is, essentially. They'd take a clean 3D object, render it with realistic lighting, and then just computationally paste it into a real background image.
So you get a plausible-looking photo, but...
You have perfect 3D ground truth for the object you just pasted in. And they made a massive data set this way, 61 million samples. That became the engine for teaching the model about the real world.
That gets you volume, but I imagine there's still a gap between a pasted object and a real one. Which brings us to the second insight, the human and model-in-the-loop pipeline, the MITL.
Right. And this is the truly clever part. The MITL pipeline changes the human's job from a creator to a verifier.
What does that mean in practice?
They realize that a regular person can't make a 3D mesh from scratch. But they can definitely look at 5 different 3D models a computer proposes and say, that one's the best.
And then just tweak its position a little.
Exactly. They just select the best candidate and refine its pose, the rotation, translation, and scale. So you go from a 4-hour job to a 4-minute job.
And that creates what they call a virtuous cycle, right?
It's a self-improving data factory. The humans vet the model's proposals. That vetted high-quality data then gets used to train the next version of the model.
which then generates even better proposals for the humans.
Making their job faster and more accurate over time. It just keeps getting better.
The scale they reached is just wild. The paper says they annotated something like 3.14 million meshes this way. How does having that much data change how you can even train a model?
It means you can finally use the training playbook from large language models. This multi-stage recipe, building up skills step by step, is what lets you bridge that huge data gap that 3D has always had compared to text or 2D images.
Okay, so let's walk through that. What's step one, the foundation?
Step one is pre-training. This is about building a foundational vocabulary. They used a huge synthetic data set, ISO3DO, with 2.7 million clean, isolated 3D meshes.
So this is just teaching the model what a chair is, what a car is, in a perfect, clean 3D environment.
Exactly. It's learning a rich vocabulary of shape and texture with none of the mess of the real world yet.
Okay, so that's the what. Then comes mid-training with those 61 million render paste samples. What does that teach the model?
That stage teaches it how to handle the real world. This is where it learns about occlusion, how to complete a shape when part of it is hidden. It learns to follow masks, and critically, it learns layout estimation.
Getting the position and the size right.
Right. It's building a really sophisticated guesser, but it's still just a guesser trained on synthetic data.
And that's where you get those slightly off results, the uncanny valley of 3D. So the final stage, post-training, has to bridge that final gap to reality.
Correct. Step two is all about real-world alignment, and they do it in two phases. First is supervised fine-tuning, or SFT.
And that uses the human-vetted MITL data?
That data, plus a small, super high-quality data set made by artists for the really hard cases where the model kept failing. This fine-tuning teaches it all the nuance it missed.
And then comes the second phase, which feels very LLM-inspired. Direct preference optimization, DPO.
Exactly. This is the final alignment. They take all those human preference rankings in the pipeline, when the annotator said this one is better than that one, and they train the model directly on those preferences.
So it's not just about being technically accurate, it's about matching human aesthetic judgment.
Yes. It's crucial for getting rid of all those common, annoying 3D generation failures.
Like what? Give me a concrete example.
The classic ones are the floater, or the bottomless mesh. A floater is a chair that looks perfect, but it's hovering an inch off the ground.
Right, violating gravity.
Or a bottomless mesh, like a bowl that's just a rim with no base. Looks completely wrong to us. DPO teaches the model an implicit sense of physics and completeness, because humans consistently rank the floating chair as worse than the one on the floor.
That's a fascinating way to use human feedback. So we have the data engine, we have the training recipe. Let's talk about the machine itself, the architecture. It's a two-stage system. Can you break that down?
Sure. It's built for specialization. Stage one is the big geometry model. It's about 1.2 billion parameters. And its job is to predict the object's poso, rotation, translation, scale, and its coarse shape.
Coarse shape, not the final detailed mesh.
Not yet. It predicts the shape using voxels. Think of them like 3D pixels. It's much more efficient to get the basic structure right first in a 64 by 64 by 64 grid before you worry about all the tiny details.
And to handle all those different inputs and outputs, they use something called a mixture of transformers, or MOT.
Yeah, you can think of MOT like having different specialist departments inside the AI. Some transformers are experts on image features, others on predicting pose. But they all talk to each other through a shared attention layer. It's very efficient.
Okay, so the geometry model gets the big picture right, the structure, the placement. Then what does the second, smaller stage do?
That's the texture and refinement model. It's about 600 million parameters. It takes that coarse voxel shape from stage one and does the detail work.
The finishing touches.
It refines the geometry to a higher resolution and, most importantly, it synthesizes the high-fidelity texture. It's the artist who comes in to polish the engineer's blueprint.
And the whole system is fed features from Dino V2, looking at both the cropped object and the full image. Why is that distinction so important?
You need both. The cropped view gives you the high-resolution details, the texture of a fabric, but the full image provides the global context. Without it, the model might see a tire in a garage and reconstruct it as just a flat disk.
Because it doesn't have the context of the car it's attached to.
Exactly. They also mentioned it can optionally take in a rough point cloud, say from LiDAR, to help anchor its predictions even more solidly.
So an unprecedented data pipeline, a specialized architecture. Did it actually work? What were the results?
Oh, the results were profound. Especially in human preference tests, SAM3D had at least a 5-1 win rate over other state-of-the-art methods on real images.
A 5-to-1 win rate, that's
Yeah.
a blowout.
It is. When you put the outputs side by side, humans just overwhelmingly preferred the SAM3D reconstructions.
And they actually had to build a new benchmark to even test it properly, didn't they?
They did. The old benchmarks were too simple, mostly synthetic stuff. So they created the SA3DIO benchmark with 1,000 artist-made meshes from really complex real-world images, ski lifts, animals, cluttered rooms. It really forces the models to prove they can handle the wild.
And the improvements in metrics were just as dramatic, especially for layout. Can you give us an example there?
The layout estimation is probably the most shocking improvement. On the Area Digital Twin dataset, there's a metric called ADDS at 0.1.
Let's quickly define that for everyone.
It basically measures the percentage of objects you place within 10 centimeters of their true location. It's a tough, high-accuracy measure.
And previous models.
Previous models were getting a, 2% accuracy. They just couldn't do it.
And SAM3D.
By predicting shape and layout together, SAM3D pushed that number from 2% all the way to 77%.
77%? That's not an improvement. That's a different category altogether.
It's a monumental leap. It means the model can actually place objects in a scene with enough accuracy to be useful for things like robotics or AR.
That level of robustness is exactly what you need to unlock those applications. Spatial computing, robotics. This feels foundational.
It's huge. But, the researchers were also really upfront about the current limitations. It's not perfect.
So what are the biggest hurdles still left?
The main one is resolution. Because it uses that coarse 64-cube voxel grid, if you're reconstructing a big scene that has a person in it, the amount of detail for small parts like their hands or face is pretty limited.
So you get blocky hands.
You can get artifacts, yeah. They note that if you crop in on just the hand, the reconstruction is much better because it gets the full resolution budget. The other big thing is scene understanding.
How is that?
It reconstructs objects one by one. It doesn't really reason about how they interact. It doesn't know about physics, like if objects are actually touching or if one is stable on top of another.
It can't tell if a book is actually resting on the shelf or just floating near it.
Exactly. It's working from visual cues, not physical laws.
That limitation actually gives us a really crucial point to leave our listeners with. A final thought.
Go for it.
So SAM3D can reconstruct a cluttered scene with incredible accuracy. The shape, the texture, the location of every object. But if it can't reason about whether a stack of books will fall over, or if a lamp is actually touching the table, if it can't reason about physics, what critical knowledge about interaction does it still lack before it can truly claim to understand that scene? That's something to mull over.
And before we go, if this conversation about computer vision and AI has sparked your interest, we really urge you to enroll in opencv.org University to get started in computer vision and AI.
That wraps up our deep dive into the SAM3D paper and the single-image 3D revolution. Thank you for joining us, and be sure to subscribe so you don't miss our next exploration of the cutting edge of research.